there we go. Okay, cool. All right, so we're going to pick up roughly where we left off last time. I'm going to review a little bit of what we discussed and think about what it means looking ahead. So last time we were examining the phenomenon of how do you get a circuit to remember something, okay? And the key insight is that if the circuit loops back on itself and uses one of its outputs as an input, it can actually have a memory just by setting up the logic correctly. And so we saw how just using a simple and, or, and not gate, we were able to set up this circuit, this SR latch. SR latch. That's a basic remember one item of data circuit. And so just to briefly review the SR latch, it's based on having a set input, a reset input, and then an output. And so if the set input and reset inputs are both 0, then the output is just what the input had been. If the set is a 1 and the reset is a 0, then the output will be a 1. If the set is 0 and the reset's a 1, then the output's a 0. And if they're both 1s, this is generally considered bad, but we rigged the circuit to make it do a reset. So that SR latch, which again we were able to build just by using an AND gate, an OR gate, and a NOT gate with this loop back input, is by itself enough to have memory, but it doesn't have everything we need to get the computer behaving precisely the way that we want. Specifically, what we really want to do is have a way of saying, if some circuit is outputting a bit, we want to save the thing it's outputting, whatever it happens to be. And so that's why we built on top of the SR latch, the D latch. And so the idea of the D latch was to say, we've got a data input and we've got a load input. The idea being, if the load is a 0, we just go with whatever we remember. We just go with the thing that's remembered. But if the load is a 1, then the output becomes whatever that data input was. And we found that, just by setting up a couple of logic gates, we could translate these data load combinations into SR combinations. And that gave us this idea of the D latch, the data latch. So that was sort of the second phase of making this all work. The third phase of making this all work is recognizing that all of our memory updates need to be synchronized. That is, we want all memory updates to happen at the same time, so that we've got some notion of a cycle in which all memory updates happen, everything can become stable, and once everything is stable, we have a whole new round of calculations, and then we do a whole another round of memory updates. In order to ensure things are synchronized, we have to have the notion of a clock. And so this clock is just a quartz crystal that when a current is applied to it has a regular pulse. And I again continue to be astonished at the idea that we can synthesize such things that will pulse billions of times per second. So what we looked at from here then was, given this notion of a clock that's pulsing, how do we set up our D latches to synchronize? And so to that end, we set up a circuit with the notion of a data input and then a notion of a clock. And so we used 2 D latches to make this work. And so our clock Input looks kind of like that. And then we've got this other D latch over here. And then we got our load over here. And the clock goes in there, and this output goes into that input. And there we are. So the really crucial insight here is the idea of taking this clock signal, splitting it, and negating one of them, then having two D flip-flops in place. So what does this enable us to do? All pending computations, when the clock is 0, basically you're stuffing data into this flip-flop right here. But that data isn't allowed to progress over here until that clock goes to a 1. When that clock goes to a 1, this data can flow freely into here, but because the clock went to a 1, this load becomes a 0, and this one is then protected from other data trying to get in. And this relatively simple arrangement allows us to ensure that all of our data accesses are synchronized. And so this circuit here is known as a D flip-flop. A D flip-flop. Now, following the NAND to Tetris theme, through this series of examples of building up the memory circuits, you can see conceptually how we went from NAND to this level. In terms of what you're going to be building, you can consider the D flip-flop to be a primitive. That is, you don't have to engineer these things. The D flip-flop is going to be provided. My goal then for the second half of yesterday and what I just reviewed today was for you all to understand that there's nothing terribly magical about the D flip-flop. It, again, is just lots of NAND gates. But it was kind of outside the scope of what's realistic to accomplish in the course for you all to rediscover the D flip-flop and how that's engineered. There are some real subtleties here. But yeah, this D flip-flop then is going to be the basis on which you build a memory system. And so each D flip-flop has a data input and a clock input. We're going to hold that thought for now. I'm going to talk a bit about what we mean when we talk about a computer's main memory. And then we'll talk about putting these pieces back together and thinking about the relationship between that main memory and the D flip-flop. So any questions thus far? All right, cool. So we're just going to spend some time thinking about RAM. We tend to take RAM kind of for granted, but we're not going to really have computers without it in any meaningful way. So we're going to think about every term that comprises the RAM acronym, right? We have 3 letters. The R stands for random. The A stands for access, and the M stands for memory. So we'll just take it as a premise that when we're thinking about the memory part, that will ultimately be expressed in terms of the D flip-flop. We're going to put that aside for now. And I really want to think more about this first part, the random access. The random access. We see a word like random, and we immediately have connotations of throwing dice, playing cards, Vegas. Innocent's got a Vegas jacket on, in fact. Have you been to Vegas?
I was there this Christmas break, actually.
Oh, okay.
Yeah.
I hope you didn't lose too much money.
I lose some.
Yeah. As long as you got a budget, you're okay. That's kind of the approach. But one of my wife's cousins lives there, so we've been out there and visited. But in any event, so random has all these connotations. That's not really what we mean here. And a clue that that's not really what we mean here is the last thing we want is for our computers to behave randomly. That is to say, unpredictably, right? It's like, I just put a value in an array, and maybe it's there, and maybe it's not. After all, it's random access. That's really not what we mean. Okay. by random here, I want you to think more in terms of arbitrary, right? Like if I throw a die and some value comes up, because I don't have a notion of a model in my mind to accurately predict what that's going to look like, the result appears arbitrary, very subjective. Similarly, from the point of view of a memory system, what the random and RAM suggests is that whatever the request coming in happens to be is similarly arbitrary. So from the point of view of the memory system, a client, a user, could be asking for memory from anywhere. And it needs to respond in a uniform way, the same way, regardless of what comes in. So we're actually going to go a bit higher level than we've been for a few moments so that we can really think deeply about what this all implies. And when I say go to a higher level for a moment, what I mean is I want to review the concept of an array. So at this point in your computing careers, all of you have managed to make extensive use of arrays. As you, in the 150 class, the list in Python is a thinly disguised array. What do I mean by thinly disguised? It's really more like the array list in Java because you can just kind of add stuff. But in Java, that basic array, I mean, that's as low level as it gets. And what I mean by that is you basically say, computer, reserve for me some consecutive section of memory and then just let me stash data there. Now, as you saw in the data structures class, once you have arrays, there's some really amazing stuff you can do to organize your data. Once you've got arrays, I mean, first and foremost, the array list, the resizable array, is kind of a nice basic means of collecting data. The hash table, of course, is an extraordinarily powerful data structure that is built on the notion of an array. The idea of a heap, a priority queue, that was also built on an array. So as long as we can get up to the level of something like an array, all kinds of things become possible. So, but what does it really mean, right? So if I ask for an array in Java, I say something like this, int bracket nums equals new int, and then I got to give it a number like 10 or really seemingly anything. So what this means is that I've requested and received a consecutive block of memory locations. But this really then causes us to think about, so if I say this is a consecutive block of memory locations, there are some extremely loaded terms in here that we really need to unpack. The first being consecutive, and the second being memory location. So what we're exploring in chapter 3 here is to understand at the deepest possible level what these ideas entail. And we're actually going to start with the idea of a memory location. And we're going to think about consecutive after that. So if I'm thinking about the idea of a memory location is basically an integer. But in terms of thinking about hardware, we naturally want to think of this integer as a binary number. Now, what am I getting at there? What we want is to set up a circuit that lets us take some binary number representing a memory location. And once we have that number, we either want to be able to read or write data to that location. Or rather, we want to be able to read and write data to that location. We want to choose, We want both options, both the reading and the writing. So this has some interesting implications. First and foremost, since this is ultimately going to be a binary number, it causes us to ponder, how many of these things do we get, right? So as I'll be doing throughout the semester and have already been doing, one of the reference points I'm going to use here is the first computer I really learned well, the Commodore 64. So let me give you a brief introduction to the memory layout of a Commodore 64. The Commodore 64 had a 16-bit address bus. Now, we've gotten used to the term bus recently because we've gotten to experience bus errors when wiring our circuits, right? So a bus is just a collection of bits conveying information that's being connected in some way, being transmitted, right? So if the Commodore 64 had a 16-bit address bus, and each combination of bits represents a unique and distinct memory location, we would say then that it had 2 to the 16th power memory locations. And each of these locations is commonly called an address. It's commonly called an address. So let's think a bit about how this presence of a 16-bit address bus interacted with how the machine was marketed. So 2 to the 16th power happens to be 65,536. And so what's at each of these things? Well, in the Commodore 64, it had a 16-bit address bus, but it also had an 8-bit data bus. So 2 different buses, the address bus and the data bus. Because it had an 8-bit data bus, every memory address contained an 8-bit value. An 8-bit value. So each 8-bit value is commonly known as a byte. In case you're wondering, a 4-bit value, this isn't a term that's commonly used these days because we don't tend to deal with 4-bit values very much, but just so you know, a 4-bit value is called a nibble, and it's spelled like that. I'm absolutely dead serious about this. Yeah. But in any event, so the byte was the data unit that was present at each of these 65,536 memory locations. Now, if we want to think about sizes of bytes, groups of bytes, a unit of measure that is commonly used is the kilobyte, or was commonly used then. And you might think that's 1,000 bytes, but it's not. It's actually 2 to the 10 bytes, or in other words, 1,024. So now we'll do a little bit of algebra. If a kilobyte is 2 to the 10 bytes, and you've got a 16-bit address space, and you're wondering, well, how many kilobytes do you get? You divide 2 to the 16th by 2 to the 10th, which gives you 2 to the 6th, which is 64. And so the Commodore 64 was a 64 kilobyte machine. And that's where they came up with the catchy name, was exactly that way. So it had 64 kilobytes of addressable memory. When you think in modern terms, it's like, wow, that's not really very much. Make no mistake, one could have a tremendous amount of fun with 64 kilobytes. The Commodore 64 was well known for having a lot of great video games to play on it that were entirely implementable with these resources. Were they first-person shooters? Well, no. But you could do some really nice 2D stuff, and they did. But still, it's kind of shocking to think about how little memory that really was. So we still tend to think about memory sizes in terms of bytes. Now we tend to talk more about megabytes and gigabytes. But we still think of them in terms of bytes. And those terms like megabyte and gigabyte, we still reckon in powers of 2, you know. So a megabyte will be 2 to the 20 bytes, and a gigabyte will be 2 to the 30th bytes, for example. Well, this has some interesting implications of its own. If you have a 32-bit address bus, you can address up to 4 gigabytes. Because if you've got the 32-bit address bus, it's got 2 to the 32nd distinct addresses. The gigabyte is 2 to the 30 bytes. That means you can have 2 squared gigabytes that are addressable. And that's a lot of why now modern machines are actually using 64-bit address buses. Because we want to be able to address more than 4 gigabytes of RAM. Yeah. And at this point, they're also going with 64-bit data buses as well. So the term for the size of the data bus is called a word. So on the Commodore 64, a word was 8 bits, 1 byte. On a modern machine, a word will typically be 64 bits. A word actually winds up being 8 bytes. And this too has interesting implications. In a high-level programming language, you really want to set up your data types to align with the word size of the underlying architecture. You know, because it actually would take quite a bit of computation to say, pack 8 distinct bytes into a single word on a 64-bit machine. You know, typically, if you're just dealing in terms of bytes, you're actually just going to use a full 64-bit word to represent each byte. That is to say, memory is cheaper than time. And so compressing and uncompressing the stuff just doesn't tend to be worth it. Curiously, though, our programming languages tend to lag this. So in Java terms, you know, the long is actually a full 64-bit int. Okay, but an int is kind of a pathetic 32 bits, and a short, which you've probably never ever used, is 16 bits. In fact, the only reason you ever use an int is that when Java was developed in the 90s, 32 bits was the most common word size, and 16-bit machines were still out there. And so because 32 bits was the most common word size, the whole API for the language was set up in terms of ints, right? Like int hash code. There's no going back on that. In Java, every class has an int hash code method. And it's not going to be anything other than an int. Now on a modern machine, it's actually kind of silly, almost quaintly silly. Like, these poor naive people, they should have just done everything in 64 bits. They should have looked ahead to the future. But they didn't. Anyway. Yeah?
What would be a better advantage of using a 64-bit int hash code instead of a 32-bit?
So let's actually talk about that. I think that's a great question. You know, what's the benefit of having a 64-bit hash code instead of a 32-bit hash code? On one level, the advantage is fairly transparent. That is, if you've got a 64-bit hash code instead of a 32-bit hash code, you have many fewer collisions, right? You've got the potential, depending if you've got a good hash code definition, of many fewer collisions. Of course, the disadvantage, or ameliorating this, suggests that, well, to make full use of a 64-bit hash code requires a hash table that's more than 4 gigabytes in size, right? You know. So there's a sense in which maybe you don't need to access it. On the other hand, given that we now have computers with RAM in excess of 4 gigabytes, it's entirely imaginable that one could set up an in-memory database with more than that number of entries. So there it is. If you had a database with information about, say, every person on Earth, and you had a hash code that hashed to 64 bits, and you had a scheme that somehow allowed you to turn the data of every person on Earth into a unique 64-bit integer, then you've got immediate access. No collision resolution. So, yeah, so it's a reason, yeah.
Can you go another follow-up question on that?
Yeah.
I feel like that's not like a very powerful idea that big companies like Google and Microsoft could use. Is there like a way someone can override, let's say, like a Java implementation to make their own?
So what you could do is define your own long hash interface that has a hash code type method that returns a long, and then you could build your own long hash map that uses that method, and then you create your own string, say, that's just like a regular Java string, but it's got the 64-bit hash code. And then, yeah, you could totally do it.
Oh, so it's doable.
It's doable. It's just inconvenient. But part of the genius of Java, some of the flexibility of Java is because you can arbitrarily define data types, you can actually code around this stuff. Yeah. And in case you're wondering, do companies like Google like to do that? Well, yes. If what the language API provides is not sufficient, they'll define their own. A pretty hilarious example of this is back in the late 80s, when Microsoft was developing the Excel spreadsheet. They wrote it in the C language. They didn't really trust what compilers were available to generate the code that they thought they needed. So the Excel group developed their own C compiler. And they engineered the compiler to have precisely the optimizations they wanted to maximize the performance of Excel. So if you've got a product that has a sufficient level of financial value for a company, and the company has the resources, they will spend seemingly arbitrary sums of money to support that product. And if you're Microsoft, well, yes, you can go and hire the 5 best compiler designers you can find anywhere and bring them in-house to craft an Excel compiler. Yeah, they can do that, and they do that, in fact. For those of you who have either taken programming languages or in the functional programming class now, a fun tidbit here is at one point, Microsoft just wanted to make sure that their company investment in functional programming enabled them to keep tabs on where it was going. So they hired away like the lead developer of the Haskell language, set him up with a research lab in the UK somewhere where he lived, and then just said, we're supporting you arbitrarily in your work on Haskell. Just go, do whatever you think is interesting, and just keep us in the loop. I'm absolutely serious about this. And Dr. Yorgi actually did a summer internship with the guy at one point. I think when he was in graduate school. Yeah. So yeah, really big companies, when it comes to stuff like that, yeah, they will throw money arbitrarily at projects in order to make sure that they have what they need to do their work. Yeah. So long answer, but kind of a fun one. So in any event, all of this background is just to say that when you allocate an array a consecutive block of memory locations, what you're doing is saying to the operating system, find some memory address where there are this number of consecutive addresses available. And one of the jobs of an operating system, and we'll see this in chapter 12 in this book, is to actually maintain a list of which RAM locations are reserved and which ones are available. And it's called the heap. And that's different than a priority queue. Like, we use heap in two ways. Sorry about that. So whenever you use new in a language like Java, that's doing what's called a heap allocation. In other words, you're reserving some consecutive block of memory addresses. So whenever we get an array, that's what we're doing, is we're asking for a block of consecutive memory addresses of that size. Now, what does that enable us to do? So here we're going to think more about the idea of an array. So I've got my array. It's called nums. It stores 10 words. We're just going to say it's 10 machine words of data, okay? The size of a word doesn't really matter for how we're going to think about this. So now, let's say I want the value at nums bracket 3. Let's think about what that winds up implying. Nums itself is simply a memory address. It's a memory address that is the start of the consecutive block of addresses we got when we performed the allocation. So this 3 is something that we just add to that baseline memory address to produce the memory address that contains the data that we're storing or looking for. That's all an array really is. Now notice something really important about this. And certainly in data structures we went over this, but boy, in this class we're going to nail this, okay? This calculation is independent of the size of the array, right? I can have a 10,000 element array, and I can ask for element 775, and all I'm doing is I'm taking that index and I'm adding it to that base memory address. I don't have to do 775 operations to get there. It's just one add. So what's really crucial here is that all accesses to a memory address should take the same amount of time. So now, from our perspective in this class, we need to think about how do we engineer a circuit to enable this, right? We need to develop circuitry that lets us feed in a memory address and either perform a write or perform a read on that memory address, such that what the address actually is doesn't really matter in terms of computation time. So when we talk about constructing a RAM circuit, this address says to the circuit, give me this value, or let me store this value. And that's what RAM is about. Yeah.
Question. So the way it sounds like nums 3 itself is a memory address.
Yep.
But when you try to create a thing at index 3, you also give it another int value, because the memory address was also a value. It adds them and then it gives you a thing on that additional.
Right. So nums is an address,
Yes.
and then 3 is an offset.
Mm-hmm.
So you add them to get a final address.
And the question is, on that address that you get,
Yeah.
is it like another location in a table somewhere, or the address itself is the value that you want?
The address itself tells you where you're going to store some data or retrieve some data. So the address is going to be an input to the RAM circuit saying, this is the memory location I want to manipulate.
I guess maybe the question is, if it tells me how to store or get data, that means there is another place where things are being stored. Like,
so there's a number of places equal to the number of memory addresses. That's how many places there are to store things. What we're doing here is saying, which of those places do we want? So reasoning about it, nums, the start of the array, is just saying this is where these places start. And the index is saying this is how far in we're going to go. So an array is kind of virtually a table, right? Because that's all it's doing. And now what we're going to be thinking about is how do we implement that table as a circuit? Yeah, good question, real good question. Something else that falls out of this, right, is why arrays start at 0. Nums bracket 0 just means take the memory address for where the array starts, add 0 to it, and use that. So that's why arrays start at 0. Like, there's nothing deeper than that. But, you know, it became the habit, right? And so now that's what we do. And of course, the very first memory location has to be 0. Because when we think about binary, and even strictly positive binary numbers, let's imagine 4 bits, right? So if I've got let's say I've got a 4-bit address bus. Well, the very first address is 0000 or 0. And the very last address is all ones or 15, right? 8 plus 4 plus 2 plus 1, 15. So there's a nice symmetry actually between the idea of the 0-based indexing of the array and the overall address space. Phrased differently, you can think of the address space as a whole as a single giant array. That's what the RAM of a computer fundamentally is. An array in a high-level language is just saying, give me this piece of it. But once we're dealing with an array, we're very close to the hardware. Very, very close to the hardware. Later in the course, when we work on our compiler, we will, of course, implement arrays, and you'll actually do this stuff. You'll actually generate the code to do this. We're not quite there yet. We don't even have a computer yet. But we're getting there. Okay. Cool. So any questions up to here before we start thinking about the actual circuits that we're going to be developing? All right. So first circuit you're going to develop is called a bit. The first circuit you're going to develop is called a bit. And you might be wondering, how is this different than a D flip-flop? Bless you. And part of what might be a little confusing about this is we know that a D flip-flop will store a 0 or a 1. We know that a single bit stores a 0 or a 1. So here's the distinction between them. And it's important to understand this distinction. A bit has one extra input in comparison to the D flip-flop. Why? What do I mean? The D flip-flop, it has data and it has a clock input. So the bit also has the data and the clock, but it additionally has a load input. So what is that about? You might remember the D latch had a load input, and then what we did was we used that load input with 2 D latches in order to enable the clock to do its job. Right. A bit then brings back the idea of the load input. And the reason it brings back that idea is that we don't always want to store the value that's coming in on the data bus. So, what do I mean by that? Ultimately, there is going to be information coming out of the ALU that's being stored in RAM. Essentially, all data that ever makes it to RAM goes through your ALU on your CPU. So you're going to have circuitry that connects the output bus of your ALU, which you all know is a 16-bit output bus. You've all just been there. There's going to be a circuit that connects that output bus to every location in RAM. And here's the kicker. You don't want to write all of them simultaneously, do you? What if you did? How bad would that be? Well, it would mean every memory location would have the exact same value. I mean, it's kind of hilarious, but not terribly useful, right? So because the ALU is connected to every memory location, we want to be able to control when the data from the ALU is actually allowed to change the memory. And that's why we have a load bit. We only allow a memory location to change when that load bit is a 1. Why? Because data is just knocking on the door of that RAM at all times, asking to come in. You know? I mean, it's kind of a funny way to think about it, but it's literally what happens in the CPU. It's wired so that the ALU is simultaneously trying to change every memory location to conform to its will. Right. But we only want to allow one word at a time to change. That's why we need a load bit. Yeah.
This might probably not be like very much with what we're talking about, but in concurrency, like any concurrency is happening.
Yeah, go ahead.
Yeah, like don't you change a lot of things at the same time?
So, Innocent's bringing up a really great question, which is, if you have concurrent data access, aren't you changing a lot of things at one time? And the answer is yes, but not that many. And here's what I mean. So our CPU is going to have one core, okay? Because we're just learning what a CPU is in this class. A modern CPU, as you all know, has multiple cores, right? So Innocent, how many cores did your last computing purchase have?
4 cores?
4 cores? Yeah. So 4 is pretty common. So let's think about what 4 cores means. 4 cores means 4 different machine language programs can all be running at the same time, which means each of the 4 cores has its own ALU. Very interesting. So you have not only one ALU trying simultaneously to change all memory locations, now you have 4 ALUs simultaneously trying to change all memory locations. So it follows from this that engineering a multi-core CPU is tricky, right? You don't want the bits to get scrambled, and so you have to do some kind of data synchronization to keep this from happening. The way this actually happens on a multi-core CPU is complicated. I'll just leave it as complicated for now. Time permitting, I might go into the details, which are interesting. But then there's an issue that's closely related to this, which is even if you've got a 4-core CPU, in principle, you can have more than one thread running in a program. In other words, in Java, for example, you can set up your program so that multiple threads are going, each of which is independently performing a computation. On the one hand, this isn't really a problem because what happens is one CPU can run, say, 50 threads just by running one thread for a little while, stopping it, running another one for a little while, and so forth. But there's actually a really deep software engineering problem there where you want to make sure that your different threads aren't fighting over who's tackling a particular address. Yeah, Caleb.
Is that why when you're coding anything that actually displays, like for instance, when you code a game, you have to have you have to have one thread that codes your like ticks and your like load times and your input times. You have to have one thread for that.
Yeah. So what Caleb's getting at is in a game, you typically have one thread of computation that's like updating your screen. You've got another thread that's monitoring your input ports, all kinds of stuff like that. Yeah, that stuff winds up being really important. So in my operating systems class, we dive into these issues in tremendous detail. Yeah. And so that's a class I'll be teaching next year. In this class, we're not really going to look at concurrency much. In that class, we look at concurrency until we're blue in the face, pretty much. Because concurrency winds up affecting a lot of low-level systems on a modern machine. Yeah, great question. So anyway, yeah, that's why we need the load bit, is to control who's getting changed. So the bit is the first circuit that you'll build in Project 3. It's not all that hard, right? You're given the D flip-flop. You just need to make sure that it doesn't get updated unless that load bit is up. So the next circuit you're going to build is called a register. And so what's in a register? It has a 16-bit input. It has a load bit and a 16-bit output. So the analogy between bit and register is like that between and 16. So a register is literally 16 bits. So we're going to have a 16-bit word size on our machine, okay? And the register chip is going to be that word that we're going to be accessing, storing, manipulating. The 16 bits only have one load bit, which makes sense because either you're changing all 16 or none of them. Why? Because ultimately that register is wired to the ALU. Maybe with some other things in between, right? But ultimately it's wired to the ALU. The ALU has a 16-bit output bus. This has a 16-bit input bus, but you only change any of the 16 bits when that load is a 1. When that load is a 0, this thing needs to be left completely alone. So once you have a register, everything else you're doing in chapter 3 is the RAM chips. So what are these going to look like? So there are 5 of these that you're going to design of increasing size. So the first one you're going to design is called RAM 8. Okay, so RAM 8 is going to be set up as follows. It's going to have the input, which is 16. Then it's going to have load, which is just 1 bit. Okay. Then it's going to have an address bus. It's going to have an address bus. Now, the name of this chip is RAM 8. How many bits do you all think it's going to have on the address bus? 8 bits? Oh, I think we can do less than that. Like, why 3? Bingo. Or in other words, log base 2 of 8 is 3. Yeah. So RAM 8 is going to have 3 address bits. So the work you do on this chip is the heart of understanding how addresses are implemented by a circuit. And that's an exercise for you all. But here's the specification, right? You have a 16-bit input, you have 1 load bit, and you've got 3 address bits. And of course, you've also got a 16-bit output, right? So the address bits control which of the 8 memory locations in it. So it'll have 8 registers, right? It'll control which of the 8 is written and which of the 8 is read. Something that'll help simplify how you think about this is imagine it's just always read. So the memory is that memory location is continuously being read. Phrased differently, whichever address you pick, that register's output is the output for the RAM 8. Okay. So it's constantly being read. Constantly being read. Okay. But it's not constantly being written. And that's where the load bit comes into play. But if it were to be written, it would be that one. So that's RAM 8. It entails very careful thinking. Unsurprisingly, it might just possibly make use of things like multiplexers and demultiplexers. Maybe. Just perhaps. Hopefully that wasn't too huge a giveaway. All right. So the next chip you're going to do is RAM 64. So RAM 64 is going to have a 16-bit input, a 1-bit load. How many address bits do you expect RAM 64 to have? 6. I heard somebody say 6. Not quite sure who, but whoever said 6 was correct. Why 6? Yeah, 2 to the 6 is 64. So the RAM 64 you can build with 8 RAM 8s. Granted, if you really want, you can stick 64 registers on there and have a ball. Okay? I won't stop you, but I'll look at you really funny. No, I'm very serious about that, right? You want to use 8 RAM 8s for this. Once we get beyond the RAM 64, giving the number of registers directly does in fact become unimaginable. What do I mean by unimaginable? The next chip is RAM 512. And this will have 16 input bits and 1 load bit. How many address bits are we looking at here? 12? How'd you get 9?
I mean, I'm just going up by 30, to be honest.
Which is a good, honest answer. 2 to the 9th power is 512.
I assume.
Yeah. So that's going to have 9 address bits. Again, if you really, really want, you can put 512 registers in that chip, or you can use 8 RAM 64s. Okay. Now, this project is divided into an A and B subdirectory. The reason is that they found that using the simulated chips, if they tried to do like the 4K and the 16K, going all the way back up to the bit that you wrote, the simulator takes too long to run. So in the A subdirectory, I think you go up through 512. In the B subdirectory is where you do the 4K and the 16K. And the reason is it'll use the built-in versions instead of yours to do those. And the whole point is just to make the simulation run at a tolerable speed. So let's talk about RAM 4K. There's going to be kind of a pattern here. 16-bit input, 1-bit load. Now we're in good shape. Now we're at 12 address bits. Yeah. You knew you were getting there eventually. Yeah, absolutely. Yeah. So 4K, in other words, that is 4,096 distinct registers. And I am really, 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 really not recommending that you paste 4,096 registers into this thing. You want to use 8 RAM 512s. You really, really do. And then finally, we have RAM 16K. This is going to break our pattern. We still have 16 input. We still have a 1-bit load. But we only have 14 address bits. We didn't go to 15. 15 would have given us 32K. Fundamentally, the way that the machine language for the computer is going to work out, there is no reason to have more than 16K of RAM. And we'll see that when we get to chapter 4, why that's the case. But given the way they designed the machine language for this thing, it's not feasible to address more than 16K of RAM. It's actually going to have a 15-bit address bus, but the memory outside of the 16K of RAM is actually going to be used for I/O, for input-output. So it's going to be how we write to the screen and read the keyboard. So the scheme that we're going to be using when we get there is what is known as memory-mapped I/O. That is, every I/O device is wired so that you access it as if it were a memory location. This is a really powerful idea because it means that all a machine language instruction is ever going to do is grab a value from RAM, do some math on it, and put the value back in RAM. That's all machine language does. But if your I/O devices look like RAM to it, in other words, the input for the screen is a 16-bit input that's wired to the output of, once again, the ALU, then from the machine's point of view, you don't have to do anything special in the machine language to handle I/O. From the point of view of the I/O device, it's not much of an ask either, by which I mean, ultimately, the I/O device needs to be controlled by getting zeros and ones from a CPU. So we might as well just have it be the writing of a value. It's very straightforward. And so there we are. So that's going to be project 3. Let me review with you all kind of the timetable-y kinds of things about this, right? So here's project 3. You've got until Monday to complete this. Once you get the general idea of it, it's not going to be difficult. So you're going to do bit and register. I'll talk about PC in a moment. Then you're going to do the RAM 8, 64, 512, 4K, and 16K. When you look in the folder, I think through the 512, they're in the A, and then these are in the B. The 512 might be in the B, I don't remember. But just look at where it is and work with it from there. So that's going to be the assignment. Any questions about this before I talk about PC? PC is kind of different and interesting. We'll talk about that in a moment. Okay, so let's go ahead and talk about PC. The PC circuit is what's called the program counter. So the program counter is a very specific and important register on a CPU. I'm going to first talk about its role. And having gone over its role, I'm going to talk about what it looks like as a circuit in terms of its inputs and its outputs. But first, the role. This requires us to think about what a machine language program looks like. A machine language program consists of instructions. Each instruction is going to be expressed as a 16-bit word on this CPU. On other CPUs, instructions could be a 32-bit word. There are some CPUs where a single instruction might be multiple words. So you might have one word that says something about the instruction, another word that has some parameters for the instruction. On this CPU, to keep things simple, every instruction is a single 16-bit word. These instructions are going to be stored in a separate address space. So in other words, we're going to have our own special address space that stores all of the program instructions. What we're going to be doing with this machine specifically is conceptualizing this separate address space as ROM, read-only memory. Thought of in colloquial terms, with your permission, I'm going to grab this and use it as a demonstration. So this is a Nintendo DS, a wonderful, wonderful invention, just a fantastic game machine. And when one uses a Nintendo DS to play a game, what one does is take a cartridge and stick it in this port in the back of the DS, right? That cartridge contains a machine language program stored in read-only memory. Thanks. The computer we are developing in this class is going to be laid out very much like a Nintendo DS. Every program it runs is, in effect, stored on a cartridge that gets inserted into it. So in a separate address space from the RAM. Modern machines kind of do this and kind of don't do this, which sounds terrible. Again, if I have some extra time, maybe next class period, I'll talk about that a little bit. But to a first order approximation, a modern machine basically just has a single giant address space that contains both programs and data. Except when they don't, but yeah, modern machines are crazy complicated. Okay. But here we're going to have two separate address spaces. The program counter then is an index into the address space where programs are stored. It's an index into the address space where programs are stored. It turns out that is, I think it's a 15-bit address space. Maybe it was even 16-bit. It doesn't really matter for our purposes. So what do we want a program counter to be able to do? Okay. So the program counter, it's going to have an input bus, 16-bit. Then it's going to have a load bit, 1 bit. But then it's got two other things that are different than other registers. It has a 1-bit reset, and it has a 1-bit INC. INC. Where have we seen that recently? INC? Sounds.
Yeah,
the incrementer. Yeah. So yeah, your solution to the PC will have an INC16 on it. No question about it. So what do these things do? The reset bit sets the PC to be 0. In other words, it says, look at the machine language instruction at address 0 on your cartridge. So you think of address 0 on the cartridge as being like the first line of code. So when our simulated computer starts up, there is a cartridge plugged in, and what the CPU does is it fetches the instruction at address 0 and begins its execution there. Okay? Load. The role of load here is a little different. It kind of comes back to, once you've executed a machine language instruction, what do you do next? And there are two options, the load and the inc. What you might think of as the default is actually to rely on inc. That is, the default is when you've executed instruction 0, the next instruction you execute is going to be instruction 1. And once you've executed instruction 1, again, the program counter increments, and now you look at instruction 2. In other words, the program counter is going to be wired, have its input, or actually, not the input, the output. They also have 16-bit output. Sorry about that. This output goes into the ROM and says, this is the instruction I want. Okay? And more often than not, it's just using its incrementer to traverse in a nice linear way the instructions in the order that they arrived. Until it doesn't. And that's where load comes in. See, once again, this program counter has an input coming off of the CPU. This one isn't actually coming from the ALU, it's coming from a different part of the CPU, which we'll get to in chapters 4 and 5. But it's got an input coming off of the CPU, and that input is saying, instead of advancing by 1, grab the instruction from over here instead. And so when the load bit is a 1, instead of just going to the next instruction, it just jumps to an arbitrary instruction in the program. And this, of course, is how a machine language is ultimately able to implement looping and ifs and if-else, right? And we'll see that once we start working on our compilers, is that all a while loop really becomes is, when I get to the end, is the condition still true? Okay, well, change the program counter to point back to the start of the loop. Now, it turns out in practice, for a lot of reasons, it's a lot prettier to work with a loop than to just jump to arbitrary spots in a program. That winds up having issues associated with it. But at the machine level, that's really all that happens. Is, for the most part, programs happily just march through in order, doing the things until they're told to jump somewhere else. That's where this load bit kicks in and replaces the address in the program counter. So part of what I'm hoping you all see at this point is, as we move on now into chapter 3 and the memory, we're seeing all of the different characters lining up that we can assemble into our CPU. The ALU that you just did, bless you, does all the math, all the calculation, comparisons, arithmetic, you name it. The memory system is effectively representing variables, ultimately. It's storing data, and now we can see from the program counter, it's handling control flow. This is where we go next. So once we get to chapter 5 and looking at the CPU, what we'll be doing is taking that 16-bit instruction and farming out the different bits to determine which of these different actions happens. The result of which is to A, affect what the ALU spits out, and B, to determine how memory changes. A computer as a whole, then, is really just calculations plus change. Every cycle, the computer calculates something and it changes memory. And that's what makes a digital computer. Calculates, changes memory. 4 billion times a second. Any questions? All right, so for Monday then, get the memory working, get all those memory circuits going. As with all the assignments in this class, it's kind of good to start early. Project 3 in some ways is a little easier than Project 2, but it really kind of comes down to once you build an idea of what it means to turn a memory address into a means of referencing a specific location, the whole thing is just going to fly out. But to get to that point takes some work. And so I really, really recommend starting this one good and early. I think once you start it, you're going to find once you get past that key conceptual barrier, it's just going to fly out and you'll be ready to submit it. Sorry about the Moodle problems. The good news was they fixed it fast. Thank you everyone who emailed me saying Moodle is messed up. That was like at least a quarter of you. So good. It's really important to let me know when the stuff is handicapping you so that I in turn can complain, which I did, and so forth. So that'll do it for today. I look forward to seeing you all on Tuesday when we're going to start writing machine language programs for our CPU.